All good?
Yep, thank you.
You're welcome.
Thanks.
So for the next couple of lectures, we'll be having guest lecturers so that you see a different perspective than what I just had. Blair Tinker is with the library, and he's basically the GIS guru of University of Rochester. And he will... And he will give you an introduction to geographic information systems, which I talked about. So if you haven't done it yet, you should watch the Geospatial Revolution episodes 1 and 2. Okay, so that will give you sort of a sense of where GIS comes from and where it's going in the future. And as far as everything else, I'll leave it up to Blair.
When's the class over?
Let's do 6:05.
6:05.
Yeah,
Okay.
that'll give me a chance to
Kind of wrap things up. Okay.
Questions.
Yeah, I'm sure it'll be loaded. So I will try to keep you awake. You know, it's a rough time of day. My name is Blair. I work at the Digital Scholarship Lab. So that's over in Rush Reed's library. It's in the Humanities Center. But we're not really part of the Humanities Center. We're actually a library department. I do geographic information systems. Basically, think of it as computer mapping. We also have a text specialist that works on text encoding and working with digital text. We have a digitization specialist who's a photographer by training, but we have a 100 megapixel camera set up that she uses to photograph old documents, photographs, and other things, a lot of stuff from rare books and special collections. We have don't know what his title is, but he does 3D modeling. He works in video. He runs the video studio in Retner. And we also have a application developer programmer that works on all sorts of applications. He does a lot of computer vision. He does web apps. He does basically any programming tasks. So we kind of have a mixed match of people over there that do digitally stuff. I'm the map person. So today I'm just going to give a overview of what geographic information systems are, a little bit of a historical perspective, and then we'll talk a little bit about how this could be useful to all. And we'll kind of do that at the end, and we'll follow up with some question and answer time. So what is GIS? Stands for Geographic Information System or Geographic Information Systems, either one. And it's a system for displaying and analyzing spatial data. So it's usually considered to be a combination of software, hardware, data, people, algorithms, and methods, tools. It's really a systems type of definition. It's not just a piece of software. You need kind of all the components working together. And you can think of it a lot just like a database. Like a database will store, numbers and figures and information about phenomenon. The GIS has that, but it also includes the spatial information of those phenomenon, and it allows you to analyze that. The diagram over on the side there shows up in pretty much every GIS textbook out there, and if you just Google what is GIS, you'll see some version of this picture. But it's a good illustration. So you've got the real world down there at the bottom, and what the GIS allows you to do is to abstract layers of information from the real world and layer them up and analyze them. So the bottom layers here, we don't need to worry about them being raster, but that just means that they're basically image data. So it's a series of pixels. So you've got one layer here. This is an elevation layer where every point in that image actually has an elevation value attached with it. And then there's a layer, another raster layer. So each of these pixels has a land use code with it. And then we have some vector layers up here, which are like line drawing layers. And you've got things like parcels. So, all your cities and counties will have your property lines drawn out. Then you have a streets layer, and then you have some political divisions on the top. So the real power of geographic information systems is taking this real world down here, and you can slice out these different layers. And you can create either raster or vector layers. And then, since all of these are spatially aware and they have other information attached to them, you can analyze them both just numerically and mathematically, but also spatially. It kind of takes a regular database model and adds that whole spatial component to it. You can store huge amounts of information here, especially with the advent of Google Maps, all the satellites. You can get really huge amounts of data. Basically, anything you can store in a database, you can also add spatial on top of that. This is just a quick screenshot from a piece of GIS software. So what we have over here, it's called an attribute table. Essentially looks like an Excel spreadsheet. So that's the kind of the numbers part, the data part of this. And over here, you actually see the geometries. This is a vector layer in the background. These are census tracts for Monroe County. So you see I've highlighted one of the features here, and it highlights the corresponding row in the table. So this is kind of demonstrating that link between this spatial component here, the geometry. It knows where it lives in the real world. It can map out these lines and the attributes that are attached to that geometry. And it'll allow you to, again, analyze the numbers. If you just want to go through and just look at the numbers, you can do that. You can combine the two in really powerful ways. So who uses GIS? Who would you see employing this? Facilities management. Do we know what this is a picture of? Do you know what that is? That's our campus, our beautiful campus here. So this is data that was sort of created by our facilities department here. They actually contracted out to a architecture company to create these data sets for them. But you can see it's got high resolution aerial imagery, and then they've got, this is just showing some sidewalks and paths and some other data on there. This image actually came from a software vendor's website, kind of the main GIS software, and it's a case study for facilities management using GIS. The ironic thing is that our facilities here actually doesn't use GIS. They paid a company to create the data, but they don't have any GIS people working over there, so they don't actually do anything with it. But they're hoping to use it. And the things that they want to use it for, right now they use AutoCAD, which is good for engineering drawings. If you want to build something, you can build get drawings that are highly accurate. But they're not so great at storing spatial relationships between layers or the attributes. So what they really want to use it for is stuff like asbestos abatement. Every time they do construction on campus, since this is an old campus, there's generally going to be asbestos that they have to abate. But it happens in little bits and pieces all over campus. They don't generally do a whole building. Just when they have a construction project, they do it. Well, that's really hard actually to keep track of for a campus this size when you count all the medical center buildings, all the river campus buildings, Eastman. So they have kind of a spreadsheet kind of database with room numbers in it, but that's not really connected to the CAD drawings. So it's very hard for them to keep track of this, and they're worried that they're either going to miss things and start doing some construction in areas that hasn't been abated yet, or they're going to go in and do some asbestos abatement and find out, oh wait, we already have done this, right? So they're looking to do things like that. They could also do spatial queries with that. So they could say, show me all of the classrooms that are within 100 meters of this asbestos abatement zone. which you couldn't do with just like a regular spreadsheet. So, a lot of large organizations like universities, hospitals, et cetera, will have a GIS employee to help manage their facilities. Planning departments, this is, pretty much every city planning department or county will have some GIS staff on site. And again, it's mostly for planning and analysis. So this is a pretty typical map, city of Alexandria, and I think it's got walkable areas for play spaces. So they've mapped out all the play areas, and they've done a buffer, which is creating an area around another area. It's one of the kind of most basic GIS analyses. So they've done a buffer, and they can see like these two play areas. This little area here is really well covered because it's in two different buffers, so you can walkable to two different play areas. And over here, you can see there's a whole bunch piled up, so that's really well suited. So if they're going to make a new play area, this will help them figure out, which areas are underserved, which areas may be overserved, et cetera. Public safety, there's a crime analysis, incident mapping. A lot of police departments are utilizing this. This is a little web dashboard for a police department. So it's not only useful for tracking crimes that have already happened, but they can use it for planning purposes. So they can create mathematical models based on historical crime data. They can throw in other demographic data, socioeconomic data, weather data, and they can create predictive models to try to figure out where crime may occur. Imagine it'd be pretty useful for a police department to be able to do that type of analyses. Environmental analysis and resource management. This is kind of where GIS was created, kind of in the resource management field. Pretty much anything in environmental sciences or resource management has a spatial component to it. So if you're tracking the movement of species, if you're tracking deforestation, it's all basically map-based or spatially based. So it's just a really good fit for GIS tools. And then we talk about in the healthcare industries, a lot of it's public health. And a lot of this is it's used as a communication tool as well as an analysis tool. So, disease mapping, epidemiological studies, and other such analyses. And then business. Of course, there's money behind this. So anytime you go to, say, Wegmans and you swipe your card, and you save your 4 cents off your like $900 bill, Wegmans is doing that so that they get all your information. They're not doing it to be nice. It's a loyalty thing, but it's also an analysis thing. So they know everything that you bought. They know approximately where you live depending on how much information you give them. And that's partially why all these stores have their loyalty cards, is so they can track your behavior. And they can track it spatially as well. So, Walmart has a GIS department where they're crunching through all that data. When they want to put a new Walmart in, they are collecting data and buying data and using your use data to figure out the best place to put that new Walmart to maximize their profits. So if there's money to be made using software, they'll find a way to do it. And then academic research, scholarship. This is where I do a lot of my stuff, being at a university. But all sorts of different projects do mapping. I'm teaching a class now, and it's almost entirely environmental science students, but I'm over in the Humanities Center. So, I'll have projects like the graduate students mapping the historical locations of grocery stores in Monroe County, and mapping out access to different neighborhoods. This is a project I worked on when I was at UVA, which is mapping the Salem witch trials, where a religions professor mapped out all the people that accused people of being witches and all the people that were accused of being witches. And basically, he wrote a scholarly article positing an argument about why it happened and who was who, arguing against a previous professor who had written an article. He'd hand drawn a bunch of maps and placed a bunch of the points on the map, and then made some arguments about some socioeconomic variables causing people to be accused of being witches and being accusers. This guy was a religions professor, so he didn't believe in the economics. He thought it was based on their religion. And he actually recreated all those maps, but in a GIS, and actually found a whole bunch of errors that the previous people had done, and did a few more, was allowed to do a few more complicated analyses, and kind of came up with his own arguments. I mean, I don't know that he was right, but it was a pretty cool use of GIS anyways. So, why would you use GIS? We already talked about the money aspect of it. You can save money. Again, facilities management doesn't have to accidentally redo asbestos abatement. It could save them tons of money. You can imagine this in lots of businesses. Insurance businesses use it because they want to track the number of roof repairs after a storm. Businesses use it to track their customers. So a lot of it is based on money. And because it's getting cheaper, there are more opportunities to make money using the software. Resource management. Obviously, we have almost 7 billion people in the world now, especially over the next 50, 100 years. Arable land, water, there's going to be a lot of stressed resources. And the Earth is a really big place. So to be able to catalog and manage that, they'll be using a lot of analysis tools that are spatially oriented. And the other reason why it's getting a bit more popular now is just a lot of the technological improvements are making it a little bit more feasible. Of course, there's computing power. GIS is kind of a computing intensive operation. It's not as much as like 3D modeling or animation, but it still takes some horsepower. So in the early days, you basically need a mainframe to do even kind of basic GIS analysis. But now, CPUs are getting so fast, computers are getting cheap. You can actually do GIS on almost any decent computer. And then the data collection capabilities. Originally, the main form was taking paper maps and basically tracing them. You would put it on this big board, actually, and you would use this puck, and you would kind of trace over the features, and you would create a digital version of your paper map. But now people don't really do that very much anymore, because you've got Google driving around, they've got their cameras on their cars, they've got their GPSs in the car tracking the data. There are way more satellites up there than I think anybody could have imagined, just sucking up huge amounts of data that can all be loaded right into GIS software. The GPS, everybody's got GPS on their phone. 30 years ago, I don't think anybody would have imagined that, you could track your every movement, like every person could be tracked. All of that can be loaded in there as well. So there's just tons of sources of data now. So it's getting that data can be a lot cheaper than it used to be. So that's kind of the overview. I'm going to do like a quick history thing. I keep shortening this every year because I get stuck on it and I spend too much time on it. But yeah, no, I like this section too, but everybody falls asleep. So I'll try to move it along. Just going to give a little historical perspective here. So talking about early geography, early mapping. There's a lot of argument about when mapping first started. There are cave paintings that kind of show areas. There are the Polynesians lashed sticks together that now they've said show trade winds and different ocean currents. So at least 7,000 years BC, there was mapping going on. Probably much earlier than that. The new kind of contender for being the earliest official map is this map in Turkey. I won't try to pronounce it, but it's dated around 9000 BC. This is what it looks like. The actual map looks like that, and that's on like a stucco clay type of thing. Here's an artist's recreation of it. So when they found this, they were really excited because they were like, wow, we found this super old map, and it shows a volcano erupting at the top, and then kind of this village laid out underneath the volcano. So of course the guys that found it, you know, they wrote their papers and they were all excited about it. But then other people came in and said, no, that's not a map. That's not a village and a volcano. The bottom part, well, these people like drawing squares. That's just kind of their thing. So they just like drawing geometric figures. And you know what? They also like drawing leopards, and that's clearly just a leopard skin above it. So they kind of had this back and forth, like, yes, it's a map. No, it's just a bunch of squares. Until a geologist actually came in and pretty much solved that it is a map. About 50 miles away from where they found that map, there's a volcano that looks suspiciously like the one in the picture. And you can see the right part has blown off. And that happened right at the same time period that drawing was made. And there's even, obviously not the actual village from 9000 BC, but there actually is a village right in the same spot that was depicted there. So now people tend to think that, yeah, it probably was a map and they were drawing out this village and the volcano erupting behind it. So then we kind of jump to the origins of the official field of geography, and that goes up to the Greeks. So a lot of the early Greeks included maps and kind of geographic principles before it was actually formalized as a discipline. And a lot of times they'd be writing a history of a place or a narrative, and it would just have a lot of location information in it. And again, it wasn't formalized as geography, but it was highly spatial in nature. One thing, you know, that at least I guess I'm old, but when I was little, that I was told that people thought the Earth was flat and you'd fall off the edge if you went too far. Nobody really believed that. The Greeks, as far back as 600–700 BC, knew that the Earth was a sphere. Nobody thought the Earth was flat. The Greek philosophers were all polymaths, so they were all astronomers, mathematicians, geographers, philosophers, and again, they all just assumed the Earth was a sphere. One of the first to teach that was Pythagoras, back in, I think it was around 500 BC. So it was pretty much just kind of assumed at that time. Aristotle was the first one to kind of write it out as a proof. And it's, there's actually people today that think the Earth is flat. There's a flat Earth society. There's, I don't know, there's like a rapper that swears that the Earth is flat, and he's in a big fight with Neil deGrasse Tyson about it. But Aristotle, had some pretty convincing evidence in around 350 BC. If you see a lunar eclipse, we had one like 3 years ago. It's the first I had ever seen. You can actually see the curved shape of the Earth crossing in front of the moon. When you're standing and you're watching a ship sail away from you, it disappears over the horizon. The last thing you see is the very top of the mast, obviously because it's going over the curve of the Earth. And again, they were all astronomers. So depending on your latitude, you can see different stars. They're all at different angles from the horizon. And mathematically, the only way that could really be true is if the Earth is a sphere. So unfortunately, we've known for a long time that the Earth is a sphere. It's not really too controversial. The father of geography is Eratosthenes, around 200 BC. He did lots of mapping. He created some mathematical formulas to convert the spherical Earth into a flat map. One of his big claims to fame, at least in the geography front, was that he actually calculated the circumference of the Earth, which is pretty impressive. There's a diagram over on the right of how he did it, but he used basic trigonometry, measuring shadows at different locations, measuring the distance between and the angle of the shadows. And depending on how you translate your Greek to modern numbers, he could have been as close as 8 to 10% off on the calculation of the circumference of the Earth, which is pretty good considering he was using sticks and shadows to do that. So not only did we know it was a sphere, they actually had a pretty good idea of the size of the Earth. He also divided the Earth into climate zones, so he kind of was one of the first ones to, and the Earth was much smaller at that point. They only knew a very small portion of it, but it was still this classification of Earth into different climate zones. He also did lots of cool math stuff. He had prime number theory and other stuff that Eratosthenes did too. He's probably pretty smart. This map is by Ptolemy. He came several hundred years after Eratosthenes, around 100 AD. He's a very prominent geographer. He wrote a large multi-volume set of that included physical geography, regional geography. Again, he expounded on the zones. He also had a gazetteer. So that's a gazetteer is a listing of places and their location. So he had about 8,000 locations listed out in the book. And he also did a lot of mapping in the book. Now this map here, none of the books survived in the original form, but they were so popular that they were copied and copied and copied. So this map here, I think, is from around 1300. So about 1,200 years after Ptolemy made his first volumes, people were still reproducing those volumes and using them, which is pretty cool if you're Ptolemy. You've got a pretty long lasting impression. But unfortunately, Ptolemy should have used Eratosthenes' calculations. He did his own calculation of the circumference of the Earth, and he made the Earth about 30% smaller than it actually is. So all of his maps are all screwed up. He's got Asia going way too far east, and a very small Earth. So a lot of scholars maintain that Columbus may have actually used some of these maps when he decided that he could sail around to get to Asia, because if you use a Ptolemaic map, it's actually way closer than it actually is in real life. A lot of other people just think he was kind of an idiot, so you can kind of choose. So this was kind of the state of mapping for a long time. At the same time, the Chinese obviously were doing mapping, not as much as the Greeks. The Greeks were kind of the main mappers of the time. Europe went through, of course, the Dark Ages, where all the maps were converted to religious symbols versus actually being accurate maps. But luckily, in the Middle East, the mathematicians and the scholars there took mapping forward. Then during the Renaissance, it had a resurgence, not only in adding increased accuracy and new mathematics to maps, but also making really beautiful looking maps as well. So now I'm going to jump from just kind of geography and map making to more spatial analysis. And this is kind of where GIS comes in. So there's a very famous story that I learned when I was getting my geography degree. You learn it, a lot of beginning epidemiologists learn it. And it's about the cholera outbreak in 1854 in London. Cholera was pretty bad business back then. And there's this story about a Dr. Snow. His name's actually John Snow, and I can't say it without thinking of John Snow. But Dr. Snow was a famous epidemiologist at the time and kind of a general doctor as well. And the story goes that there was this giant, very bad cholera outbreak, and John Snow thought that everybody was getting sick from a poison well, but nobody else believed him because everybody else thought that cholera was caused just by stinky air. London in the 1850s was a pretty disgusting place. I mean, they did not have great sewers, especially in the poorer areas. Everybody was packed in. They had cattle living among people. It was pretty disgusting. And everybody just thought that cholera was caused by this really gross, disgusting air. They called it miasma. Dr. Snow thought it was from contaminated water. He'd actually done research about 5 years before this that led a lot of credence to his question, because a lot of people got their drinking water out of the Thames, and they also dumped all their sewage into the Thames as well. So people that were further inland, there was less poop in the water, basically. And then as you got closer and closer to the ocean, more and more people were putting their sewage in it. So he did an analysis looking at neighborhoods and found that neighborhoods, even if they were closer to the coast, if they got their water from upstream, there was much less likely to get cholera than people that got their water closer to the sea downstream. So he had this really strong correlation, which really indicated that it was water. He actually wrote a paper on it called On the Mode of Transmission of Cholera, and it was basically ignored. Everybody still assumed it was this nasty air. So they get this new outbreak, and he tries to tell people that he thinks there's a poisoned well, and nobody believes him. So he goes out and makes a map. And what he puts on this map is he maps out all the pumps. This is a portion of the map. It actually was quite a bit bigger, but this is the important part. He lists all the pumps where people get their water from. And then each of these bars here is somebody that died from cholera. And it's about 600 people that died in 10 days. So it's pretty bad. So he maps all this out, and he shows that it's concentrated around this pump here on Broad Street. And he goes to the town council, and he brings his map in, and he says, you know, by Jove, it's this pump here. And they say, you're right, Jon Snow. And they go out, and they take the handle off the pump, and they stop the cholera outbreak. It's an awesome story. It's at least 30% true. There was a big cholera outbreak. He was one of the only people that thought it was a waterborne ailment, but he didn't actually make the map until several months after the outbreak was over. There was another map created during the outbreak, which isn't famous. It was done by the sewer company because everybody was blaming them for the cholera outbreak. So they had a sewer employee go around and make a very similar map, only he was mapping out, instead of pumps, he was mapping out any place where their sewer gases could come out. And he basically proved the opposite of Jon Snow. He said, look, there's no relationship between our sewers and these cholera outbreaks. So this map was created several months after the outbreak. But he did actually manage to convince the board to remove the handle from that pump. And again, it was about 10 days after the outbreak had started. That pump is still there, and they've got a little, it's missing the handle, and they have a little sign describing it. But most epidemiologists and other experts think that the outbreak is pretty much done anyways. Cholera is pretty bad. Most people actually died from it. They had about an 80% fatality rate at that time. So after 10 days, either you were dead, you had moved away, or you'd already gotten cholera and were recovering. So they tended to burn out pretty quickly. But the important and lasting parts of this are the spatial analysis part. So we mapped out all the incidents, and he actually walked door to door. Not only was he collecting data, he was a doctor, and he was actually caring for people as well. So it's actually, there's a really good book called The Ghost Map that kind of describes this whole thing, which is, it's a pretty easy read, and it's an interesting story. But he actually went around with one of the local clergy and went door to door trying to treat people and collecting data at the same time. And he created this map afterwards when he was writing a paper about it. And the thing that he added to the map, some versions of the map, but not all of them, is this line here. And what that line represents is the exact midpoint between the Broad Street pump and the next closest pump. So there's a pump over here somewhere, and this line here is the halfway distance, walking distance, between the two pumps. So anybody inside this line, it's quicker for them to go to the Broad Street pump than any of the pumps outside the line. So when you map it out like this and you draw that line, you can see that there are some outliers, but the vast majority of the cases are within that line. He followed that up by actually going out and visiting all of those outliers and questioning them. And a lot of people actually just worked down in this area, so they drank out of that pump. Other people had neighbors that worked there and would bring water back for them. Or they just said that this pump, the water out of that pump tasted better. So people were willing to walk a little further to go to that pump and get their water. It's kind of disgusting because the thing that caused the outbreak was basically a baby died from a different part of England. Was the first case in here. And they had taken all the soil, the color is a messy way to go. They took all the baby soiled nasties and put it in the garbage bin, which happened to be right next to the well for that pump. And it seeped from the garbage into the water. So people were walking extra distance to get like baby diaper water. So that gives you an idea of how good the water tasted in London in 1854. He made the map, he published the paper, and it just kind of sat there. Nothing actually came up much of this until the 1920s, when an editor for an epidemiological journal was looking for a good case study that really demonstrated a lot of different epidemiological research methods, and came across this paper. So it combines firsthand data collection. He also went to City Hall and was looking at birth and death records. It's got mapping. It's got the addition of the line here of the minimum distance. So this actually combines lots of different aspects of spatial analysis into one nice, neat little package, and it's a great teaching tool. So even though lots of people were creating maps similar to this, and lots of people were doing research, he was the first one to really combine it all together into a really cogent package. So that's why it's taught today in geography departments and epidemiology schools, is the cholera outbreak in 1854. Jump ahead about 100 years to the first actual geographic information system. So it was created in Canada in 1960 by Roger Tomlinson, who worked for the Canadian Forest Service. And you know, Canada's big, they got lots of trees. In 1960, that was the main driving force for their economy. One of them was forestry. So the way they managed that was with tens of thousands of maps, stacked in map cases. And at that time, if you wanted to create something like a layered view of a map, you would take the map and lay it down. You would take a clear sheet of plastic and lay it on top of the map. And then you would find that layer that you wanted to abstract. So maybe it's oak forest. And you would take a Sharpie, or whatever the equivalent was in 1960, and you would outline the area that you were looking at. And then you think, well, actually, I want to find out the area of that oak forest that overlaps with where these lilac trees are, or whatever. You would grab another plastic sheet, lay it on the map, and draw that outline. Then you could start layering these plastic sheets on top of each other, and you put another sheet on top of that and you could draw the intersection of the two. This is all done by hand, of course, with markers and plastic sheets. And then to calculate the area, they would draw these little boxes and manually count it up, and they would be doing the calculations that way. Obviously, that is a pretty time-consuming process. It's pretty hard to do that on any large scale. And again, Canada's pretty big, so they literally had tens of thousands of maps in these map cases. There were already people doing computer mapping. A lot of that was done at Harvard in the computer graphics and spatial analysis lab. So they had created some mapping programs, but it didn't really have the database portion of it. It was really just computer mapping. And what Tomlinson did was kind of merged that computer mapping portion with the database portion and the analysis on top of it to actually create the first GIS. This is just kind of give you a sense of what the state of mapping was in 1974. So Tomlinson created the first GIS in 1960. And then by 1974, you would get a beautiful map of this, like this, a per capita income in Africa. This was created using an application called SciMap. This map probably took some hardworking person, 3 or 4 days worth of creating punch cards that they would take over to a mainframe and feed the cards in. And then you would get this beautiful map on a dot matrix printer, which you guys probably haven't even seen except for maybe in like movies or TV shows. But this page probably took several minutes just to print. And these are all just regular characters off the keyboard in just different fonts and densities to create a shaded map. And I'm sure, this person brought this map out, and they're like, oh my God, that only took you 4 days to make. People were probably blown away by this map. But I mean, that was 1974. So it took a while for the computing technology to really allow people to leverage GIS effectively. So from this point, what you have is there was a graduate student in the Harvard lab, and Jack Dangermond. He and his wife started a company called Environmental Systems Research Institute, or ESRI, or ESRI. And they created the first commercially available GIS that was basically for sale. Originally, it was kind of a mainframe type of thing. Universities and huge corporations could buy it, but they were really the only ones that had the resources to do it. It was all command line, so there's no interface. It was all just typing out commands. But it was the first thing that really made it accessible to a wide audience to be able to use GIS. It was expensive and it was difficult, but you could do it. Today, ESRI is the biggest GIS software company in the world. They have by far the largest market share of the GIS business. Their first product was called ArcInfo. Again, that was the command line software. That's what I learned on. In the early 1990s, late 1980s, they had one of the GUIs, so a desktop software that you could point and click called ArcView, and that really made it so that anybody could use GIS software. It was still fairly expensive. You still needed a really good computer to run it, but that's when you started seeing, most universities, any company could really run GIS software. There are lots of companies today that create GIS software. Again, Esri is the biggest. It's still a privately held company too, and Jack Dangermond still runs it with his wife. There's also MapInfo, which was created out near Albany, out in Troy, New York. That focuses a lot on business applications. It has like a simplified interface for business applications and market analysis. Autodesk, the company that makes AutoCAD, while they focus mainly on CAD, they also have Autodesk Map, which is their GIS application. There are lots of different companies out there doing it. You have a couple different sources. You have commercial software. So we're saying Esri, MapInfo, Manifold, Autodesk. There's Imagine, which is more image analysis. Google Earth, some people sort of put that in there. It's not really a GIS because you can't really do analysis with it. But if you're tricky, you can sort of fool with it. So some people will put Google Earth Pro in there as a commercial-based GIS software. And the characteristics of a commercial software, they often have proprietary data types. It's changing a bit now, but Esri had their own format called the shapefile that they created. Originally, it was ArcInfo coverage files, and the only software you could use it in was their software. So it was really a big investment. If you chose a GIS software, commercial software, you were kind of stuck with that software unless you want to do really expensive and painful conversions. Most of them can read kind of open source types if they really push you towards their own. They're often pretty expensive. ArcGIS can be, if you get the whole boat, can be $20,000 to get the software and all the extensions for it. But they're super powerful. They have good documentation. They've got support. Esri has a user conference every year that's got 30,000 people that show up. I don't know, it's a huge affair out in San Diego. So there's a big community, and the software is pretty amazing. On the flip side of that, you have open source software. So this is software that's usually free or cheap. If it's open source, it means the code is actually open. So if you want to go download the code and change it, you can actually upload it back to the developers and say, hey, I made these changes, and they may or may not take it, but the code is actually open. You can crack it open and look under the hood. And some examples of that, there's GDAL and OGR. These are command line tools. It's just a bunch of libraries. I actually use them quite a bit because it's good for scripting. You can write a Python script and kind of loop through a bunch of files and do different spatial stuff with it. GRASS is image analysis. Awesome is image analysis. QGIS is kind of the open source answer to ArcGIS. So it's a desktop mapping application. I use it all the time, actually. ArcGIS only runs on Windows. QGIS will run on Windows, Mac, or Linux. So it's a lot more flexible. Google Earth again. SketchUp, if you're familiar with that, it's not GIS, it's actually 3D modeling. But you can actually do some spatial stuff with it, and you can use it as kind of an add-on to GIS. I threw it in there. Again, the nice thing about these is all of these are free. All of those are multi-platform as well. But they don't have 1,000 developers sitting out in Redlands, California, developing this, and let's make this button look really nice. They have a community of people that get paid very little or nothing at all to develop these tools. So they often don't look all that nice. The menus are kind of clunky. Usability can be kind of tough. The documentation can be kind of crappy. So there are definitely drawbacks to it. The advantages are, it's completely open. So there's not some company trying to make money off you. It's a group that's trying to build tools to help other people. So in general, in academia, we love open source stuff, and we love to use that as much as possible to kind of support those communities. And it's just kind of suits our way of doing things a little better. But there are some drawbacks. Again, it's totally free, so if you're going to be doing GIS here, a lot of times if I'm working with a student and they're a junior or maybe a senior and they want to do some GIS stuff, I'll put them on the free software, because once you graduate here, you're not going to have access to ArcGIS. The university has a site license to that they pay God only knows how much money for. But if you go out and you want to do ArcGIS and you just want to buy a license for yourself, the bare minimum it's going to cost you is $1,000 for the software. I think it's probably closer to $1,300–1,400. If you want to get the same exact package that you have here, it's going to be closer to $20,000 to get the software. So we love using the open source stuff. There are a lot of specialty tools as well. Some of them are open source, some are commercial. If you're a statistician or you're using statistical packages like R, SAS, Stata, almost all of them have spatial plugins to them. So R spatial actually uses these GDAL and OGR bindings. So you can write some spatial analysis tools in R. So if you're doing some heavily statistical type of work, you might want to do it in R if you're comfortable with that. A lot of times I don't know R very well, so I'll do as much as possible in this and then kind of export the stuff to maybe do it in R at the end. Also, databases now are all kind of becoming spatially aware, so it's not quite as proprietary anymore. So, you know, if you have MySQL database, you can add spatial data in there, and they have a spatial field type now. So Oracle, SQL Server, they all have spatial components now, so you can store and analyze spatial data right in a database. So just to kind of talk about GIS here at the university, I teach a class. Like to think it's maybe a little more interesting than this intro, but maybe not. I teach it every fall. It actually takes place right before this class, or it has been. I have 16 students this time. Most of them are environmental science students, but I'd really love to get some people from the humanities and social sciences in there because, again, these are tools that are really useful across the board. I teach the only class at the university in this, so it's kind of got one shot at it. The goal of the class is to not teach the theory and all the science behind GIS, but to get you comfortable with using the tools so that you can apply the principles and the software to whatever you're doing. So that's a little plug for the GIS class. If anybody has any questions about that, I'll be around afterwards if you want to ask. So I'm the only support person on campus as well. There used to be someone in environmental science, but she left. So I'm pretty much it. But I pretty much help anybody on campus. Again, I'm over in the library, centrally located. So pretty much anybody on campus who has any questions about GIS, mapping, spatial data, anything spatial related usually gets funneled to me sooner or later. I have a friend over in IT that actually does all the software installs and licensing and all that, so luckily I don't have to do that part. But university IT actually pays for the license. It's available on River Campus. On any of the public workstations on River Campus, you can get the ArcGIS suite that we pay the site license for. So any IT maintained lab, it's under mapping and GIS, and you'll see the software under there. It's not available in the Med Center, Eastman, Warner, Business School, because they didn't want to chip in for the license. Individual users can still get the software; they just have to pay for it. It's still a discounted price, but it's not included for free. If any of you actually want it on your own personal computer, that can actually be arranged as well. And again, that's all the Esri software that we have the site license for. But again, I support all the open source tools as well. So if you have a Mac and you want to install some desktop GIS, I can get you set up with QGIS and get you set up with some tutorials, and you can actually start doing stuff if you don't want to take my class. So who cares? What am I going to do with GIS? What's the point? So I put a slide in here about GIS careers. You're probably not going to come out of U of R and hop into a GIS career because there's no geography department here. I teach the only class you can get in GIS. But definitely somebody that's technical, especially somebody in environmental sciences. If you take my class and then do some work on your own, you could definitely learn enough to get kind of a GIS intern position. This is a pretty common way to do it. So lots of architecture firms, urban planning firms will have GIS interns, and they're not expected to know a ton, just kind of basic use of the software. So you can get in there. You know, you take it if you have some GIS experience. You can get an internship, and you can really learn a ton in those positions because you're actually doing it. You're not sitting in a classroom like following exercises. You know, they put you to work there. They usually will, you know, have you shadow a more senior GIS technician or specialist. Kind of the entry level for an actual position is a technician or a specialist. That's where I started. When I graduated college, I got a job as a GIS technician at a regional planning agency in Virginia. So I just made lots of maps and did lots of basic analyses and went to lots of meetings. But it's you know, it's a good job. There are a fair number of them out there if you're mobile, if you're willing to move a little bit. I'll say the Rochester area has got some, but they can be a little bit tough to come by. But you know, those kind of jobs will do basic GIS analysis. They'll do some data creation. You know, usually kind of the more basic tasks that might be a little bit boring, but again, you don't need a whole lot of experience. You know, if you've had an internship in GIS, you could get one of those technician jobs probably. And then the next level up to GIS analyst. You just have more experience, and this is where you'd be creating data models, maybe programming. All of these software have ways where you can create your own GIS programs within a program. So ArcGIS uses Python as its preferred language. So right within the software, you could write a Python program that will, you know, grab 50 different data layers and do 20 things to each layer, and then combine them in this way or that way. And that's where the GIS analyst would be in, to be creating those tools and procedures and doing some programming. That's, you know, where I think it gets really interesting in that kind of stage. You've got the basics down from these levels here, and here you're actually applying these things, figuring out new ways of doing things, doing some basic programming, writing some scripts. You may also be working with an actual software developer that may not know any of the GIS stuff, but what I would call a real programmer, which, you know, I have a guy in my office that's a real programmer, so, you know, he and I will work together. I'll kind of do some of the spatial stuff, and he'll do the real stuff. And then, of course, you can, you know, be a GIS coordinator, or you don't get to play with the software as much. You go more to meetings and you manage a GIS department. It's a more strategic thing. Again, nothing, you can't follow this path, because again, if you took my class and you got an internship, you could probably actually do this. I mean, GIS is not rocket science. It just takes time in the software. On this campus, where I think the value really comes in is as an add-on to whatever else you're doing. So if you're in political science, there's a lot of data that's just spatial in nature. And if you have some experience with GIS, if you know how to use the tools, you're going to be able to do different analyses and different projects than if you didn't have this experience. So you may say, geez, it'd be really great if I could figure out if this voting pattern has anything to do with the unemployment rate. But, you know, without some kind of GIS experience, that's going to be very difficult to do. So it opens up a lot of doors in just about any discipline. Now, some of them, you know, some are better fitting than others, obviously, but in almost any discipline, you can find something where it'd be useful. So just in general, it's a great tool to have. It's a great skill set to have as you're going through your courses here. And then on the other side of that, when you're applying for a job in, let's say you're getting an English degree and you want to go to graduate school and you're applying to all these great graduate schools for English Lit. And you know, a lot of the applications look the same, but then yours at the bottom says, oh wait, this person also knows GIS. And look at, they did this cool project where they mapped out Mark Twain's travels and compared that to his writing and did an analysis of that. So it's something where if you know it, it can be a good differentiating tool to a lot of other people that have virtually the same qualifications that you have. This is one that you can tack on there that is not so common and is considered pretty valuable, pretty much across the spectrum. And even if they may not think it's valuable, if you get that interview, you can argue why you think it is valuable. Again, it's a tool that not a lot of people know. It's pretty technical, so it proves that you've got some level of technical capabilities that maybe other people don't have. And again, it's just another tool that you can add on to lots of different projects that you might be doing. That's all I got. I finished early this time. I usually run out of time.
And what I want to add is ESA. I think you hit on a lot of good things with regard to GIS. I sort of look at computer programming as being the same type of skill sets, but GIS is definitely something that is a little more, I don't know, I think it has a lot more appeal because of its wide uses for a lot of things.
Yeah. It's a good companion, like computer science or programming. It's a good companion.
Like the fact that you did Python there also.
Throw it in for you.
Do you have any hits from any people who want for internships from any of the?
I don't. I know some of them have internships. I think Bergman Associates. Some of the planning firms around here do have internships. A lot of them, they have a really good GIS program. I should mention this actually in Monroe Community College. They've got a good 2-year program in geospatial sciences. I don't know what it's called, but it's basically GIS. And you can get a GIS certificate if you go through the whole program. So that would actually put you, you would skip that first level and a half pretty much if you get the GIS certificate. But they have a lot of really good instructors over there. Really good kind of full program over there. So I think a lot of the jobs are taken up by those. They have a pretty good pipeline over there.
And our next guest lecturer on Thursday is Andy Mendola. Actually, he works with imagery, but he is very involved with the GIS community. So he'll sort of give you a different bent on what he presents, maybe imagery, but one of the things that I sort of wanted all of you to understand is that distinguishing the data between imagery and graphics, vector graphics, which you touched on very a little bit.
Yeah, yeah. I mean, so it's I can touch on that a little bit more. So it's I mean the two main formats with imagery. So Andy, right, is coming in. Yeah, from Pictometry. They're an aerial imagery company. I used to work for a satellite company, and we actually used to be partners, sort of, with Pictometry. But Eagle View, they are now. So again, if you have experience with Photoshop and Illustrator, that's kind of a good way to think about the data types. Raster data, it's basically pictures. So that's kind of your Photoshop data where you're going in and it's a continuous surface of pixels. And then your Adobe Illustrator would be your vector data where you have points and lines and polygons, more like drawings. GIS uses both of them, and it's doing more with imagery now. It used to be almost entirely the vector side. ArcInfo couldn't even load imagery; it was all vector stuff. So yeah, I mean, Pictometry is a great data source. They just have a ton of data available.
Can you say a little bit more about field work? Is that something that?
Yeah, sure. So I didn't show ArcGIS online. I can come back in if we want to do that before the exercise, or because I'm
after class or something.
yeah, I'm right there. So yeah, field work. There's actually again, this is getting easier. You used to have a lot of specialized training to do field work. A lot of construction companies, any kind of facilities. A lot of your time can be out in the field with a GPS doing data collection. I have a lab in the class where we go over to Mount Hope, and you can actually put ArcGIS has a mobile platform as well. So you use the GPS in your phone, so you can go out and do data collection. You upload that data to the cloud. So everything now is getting, like everything is cloud-based. So a lot of this, your data lives in the cloud, so you can have field people out in the field doing data collection, loading their data to the cloud. You can have GIS technicians back in the office accessing those data sets and doing the analysis. Field data collection also is in a lot of academic fields, so a lot of anthropologists, historians use it for archaeology. If you're out at an archaeological dig, when I did archaeology in college, we used surveying tools, so theodolites and other laser-based tools. But a lot of times now, just use a GPS to do that. So there's the sitting behind the desk part, but there's also the out in the field part, and then there's the data collection part. If you get into aerial imagery, where you're actually working on the sensors. So a lot of that in Rochester actually, because the satellite company I worked for, the optics were built in Rochester at ITT, which is now Harris Corp.
Probably some of the grads in this building.
Yeah, probably some of the optics people here. So it's actually a good town for at least the remote sensing part, which would be satellite imagery, laser, scan data, and that kind of stuff.
Thank you, Blair.
Is that it?
Yeah, it gets better and better every year.
So if anybody has any follow-up questions, if you're interested in the class, or if you just want to know anything about it, I'm right over in the library, and you can just kind of wander in. You can shoot me an email and get contact information.
We'll set up accounts for you guys to use.
Yeah, and I'll probably be back, and you guys will do a class exercise using the online tools, and we'll get you set up for that.
Right. I'll have a very short office hours tonight, so I'll probably be here for another 10-15 minutes. Fortunately or unfortunately, it's my anniversary. Oh. Now that just got recorded. I'm gonna get some points. Thanks, Mayor.
Yeah, no problem.
Did you say